Today we're going to begin the unit of kinetics, chemical kinetics. The word kinetic means movement. You've heard of kinetic energy, which is energy of movement, potential energy, stored energy. So chemical kinetics has to do with movement of the particles. And so it's making it seem like almost like a physics type chapter. If you've had physics, then you probably will enjoy kinetics. I like kinetics. So kinetics is basically just the speed, or how fast is reaction going. Does it take milliseconds for something to happen? Does it take years? We talk about nuclear decay. Some of them take millions of years for it to nuclear decay. So the study is going to be about how fast is the reaction moving forward, making products. And so some vocabulary, the collision theory, we know that the molecules are constantly moving. All molecules are moving. We know in solid form they're not moving very much. They're just kind of vibrating. In gas, they have a lot more movement, liquids in between there. So when a chemical reaction takes place, you basically have to have a collision. You have to have two molecules or atoms binding into one another, colliding with enough energy to make another compound, to break up old bonds, make new bonds with one another. And so there's two things that must happen for this to take place. And I kind of went to it. It's first that they must have enough energy to overcome something called activation energy. I would like you to know what the definition of activation energy is. Activation energy is the minimum amount of energy required for a reaction to take place. And you should have heard about that somewhere in your science career. So we label it as E. Capital E means energy, and the little a means activation energy. So we say E sub A is activation energy. And so that is the minimum amount of energy required to start a reaction. Required to start a reaction. And it's different for every reaction. So in order for any particular reaction to take place, you must overcome that minimum amount required for that particular reaction. So they're not the same. Some take, not much and they'll spark, and some it takes a long time for it to react. So activation energy, amount of energy it takes to start the reaction. And then your reactants, remember that's your starting material, they have to be correctly positioned with one another. So them colliding in the wrong orientation may not result in a reaction as well. I used to have a little animation that was online where it would show two molecules colliding, but they wouldn't hit in the right direction, so therefore we wouldn't get a reaction. So they must smash with enough energy for something to happen, and they must be correctly oriented so that something would happen as well. So basically oriented means turned in the right direction as well. So those are the two requirements for a reaction to take place. Alright, so we're going to talk about some things that will affect. We're going to talk about them in terms of speeding up the reaction, but also it could be the opposite of slowing it down. So I'm going to talk in terms of speeding up. So what's some factors that are going to help speed up a reaction? Well, again, it's about those molecules moving and bouncing into one another. And so if we have more concentration of reactants, so let's just think about cars down and going down a highway. So if you don't have a lot of cars, the likelihood of them ramming into one another is less. So for example, here in Texarkana, even though we have quite a bit of cars on the road, we don't have as many car accidents as maybe like in Austin or Houston, where it's more congested. So the higher the concentration, the more likely the molecules are going to collide into one another, and that usually typically would result in a faster reaction. So the orientation of them hitting more than one another. So concentration. If we increase the concentration, more than likely we will speed up the reaction. That is not always the case, and that's what we're going to learn when we learn rate laws. But for the most part, if you were to increase one of the concentrations, it should cause the reaction to go faster. But we will learn that that's not an always. There's never an always in chemistry. So, and the opposite of this would be is if we decrease those concentrations, and we're talking molarity here, really. Well, it doesn't have to be molarity, but most of the time we're talking about molarity. So then temperature. So, if you heat something up, those molecules are going to tend to go faster. If those molecules are going faster and they're randomly moving around, then they're more likely to bump into each other. So the faster they are, the more likely they are. Think about a hallway or just a busy, we'll just do a busy airport. Not that a lot of people are traveling right now and the airports aren't quite so busy. But if people started running around, a bunch of them, because they're going faster, they're more likely to run into other folks, right? So, and that probably could result into a reaction of some kind. So the more people, the faster they're moving, going to result in a faster reaction. The next is a catalyst. Most of you know that a catalyst is something that speeds up a reaction. So we want to talk about the two ways in which this happens, and I would like you to know the two ways a catalyst speeds up a reaction. So we know it does, okay? And an enzyme in your body is just a catalyst. So students usually will say, what's the difference between an enzyme and a catalyst? Enzyme is a catalyst in your body, and you have several enzymes. If you studied an anatomy course, or so salivary amylase is in your spit, and to help speed up your digestion. So usually if it ends in an ACE in your body, it's some sort of enzyme, some sort of catalyst. So two ways that this is going to happen. One, it is going to lower that activation energy. Remember, the activation energy is a minimum amount of energy required for a reaction to take place. Well, this is going to lower that, so it's going to take less energy. If you want to think of like a stick of dynamite, okay, a stick of dynamite, if we give it a long fuse, that would be like the activation energy, a very long fuse. And if we were to lower that, means cut that fuse in half, that's what a catalyst does. It basically lowers the amount of energy before that reaction takes place. I always give the example of I'm a pretty calm person and not much makes me upset. I don't know if that's so true right now, but not much will make, so I have what I say a long fuse. So it takes a lot of activation energy to make me really angry. But if you want to lower my activation energy, you just mess with my kids. So if you mess with my kids, that's a catalyst for me. That's going to speed up the point at which I get upset. So activation energy, catalyst will lower that activation energy, requires less energy for it to get started. Now, the other one is it gives an alternate path for the reaction. So it's kind of like a shortcut. So rather than having to go the long way around to get somewhere, it kind of gives this little sneak pathway. So that's another thing that a catalyst does. And if you're a biology major, you've learned about the lock and key mechanism for enzymes in your body. And so that's what it does. It'll temporarily lock up to the molecule, move it to where it needs to go, and then unlock. And that's kind of like what a catalyst does. So catalyst is able to speed up the reaction by those two mechanisms, lowering activation energy and giving an alternate path for the reaction. And the last is increasing the surface area for solids or liquids. I could have put it in gases too. So gas, if you put them under more pressure or decrease their volume, you would be getting them close together. But for solids or liquids, if we were to smash them up, that would be increasing the surface area. So more things would be exposed. So if it more was exposed, then it would result in more connections, more collisions going on. So basically you would smash them up, spread them out in liquid form, or smash them up in solid form to speed up the reaction. So these are all ways which we can speed up a reaction. Alright, so now, oops, it's cutting off part of my thing, so sorry, we moved it. There we go. So we're going to talk about how to, and there's a worksheet, I should have said that in the beginning, that you could fill out to go along with these notes that I've uploaded. So we're going to learn how we can calculate the rate of reaction. And again, if you've had any sort of physics class, then this kind of makes sense for speed. It's distance divided by time, or velocity, displacements divided by time. So to figure out the rate for a reaction, it is going to be the change in the amount, and this is, triangle means change in, the change in the amount divided by the change in time. So change in the amount divided by the change in time. And we have a real generic reaction here of A is turning into B. So we've got the change of A making B. So the change in the A molecule divided by time would give us the speed. How much is it reacting? So if you don't know what the little triangle means, the other way to look at this would be the final concentration minus the initial concentration, because the little triangle means change in. It's delta, which means change in, which is always the final minus the initial. You should have seen that in one of your math classes before as well. And then divided by the change in time. So we can figure out the speed of a reaction by the change in the amounts divided by the change in time. Okay. So I have this little, this came from a textbook here, so it's just a little simulation here of, this is that A turning into B, some made up thing, because we know that A is just not going to magically go into B. But do you see that the red dots, these are supposed to illustrate A, and it says we have 1 mole of A. Well, if we had 1 mole of A, we would have 6.02 times 10 to the 23rd of those A molecules. I have a feeling there's not 6.02 times 10 to the 23rd in there, but we're supposed to just use that as a simulation. So in the beginning, they're all red, and so this is at 0 time. We've got a little clock going on up here. So at 0 seconds, there is no A. And then you'll notice as time is going by, and there's no B, all A, no B, as time is going by, so 20 seconds has gone by, and now your red have turned to blue. So red is the A and B is the blue. So we've got 0.454 moles of A and 0.46 moles of B. Can you see that we still, because we have a sealed container here, that we still have a total of 1 mole? Law of conservation of mass says that we need to keep that same amount in there. If we're in a sealed container, nothing can get in and nothing can get out. So there, this is the same amount. So where did A go? Well, it turned into B. So hopefully you can see A lost 0.46 and B gained 0.46. So some more time has gone by, and now we have an amount of A of 0.3 moles of A and 0.7 moles of B. Can you see that that still equals 1 mole if I add those together? So we're going to look at a couple questions. And so let me take a picture of that before we can work. It says calculate the rate of disappearance of A over the time period of 20 to 40 seconds. So we're looking, this was 20 seconds here, and we're wanting to look for A. So we're looking at here, and we're looking at here. So that's the time frame that we want to be looking at. All right, so it wants us to find the rate. So the change in the amount of A divided by the change in time is going to get us the rate, which is what we're looking for. So the triangle means final minus initial. So the final at the latter time is 0.3, and that is moles of A, minus, because change in, 0.54 moles of A, divided by our change in time. So the time is 40 minus 20. 40 seconds minus 20 seconds will get our change. So if I subtract this, I would get a negative 0.24 moles of A, and divided by 20 seconds. Let me get my calculator. I should have already done this, but I didn't. So 0.24 divided by 20, I'm getting a 0.012, and we've got 2 sig digs. We don't use our times for this, so 0.012. It is negative, so we'll talk about that negative, moles per second. All right, so why is it negative? Do you remember our equation was A going to B? A is disappearing, B is forming. So we're losing A and we're gaining B. Does that make sense? You're losing A, going to B. You can see it with the red dots. So that's what that negative means. That negative means disappears. It's going away. So honestly, on your test, if sometimes they'll say, what is the rate of disappearance? It may not have the negative there, and Chem 101 may do the same, because the word disappear means negative. So you wouldn't necessarily have to have the negative. It just said, if it just said, what is the rate, you'd put the negative. But if it says, what's the rate of disappearance, it may or may not need the negative, depending on the question. I'm not going to try to trick you, though. So that's what that negative means. It means that A is going away. All right, so hopefully, and it's moles per second because it was moles, it was seconds. Moles per second is the rate or the speed at which this thing's going. All right, so let's look at the next question. So what would the rate be for B in that same time frame? So that same time frame, that 20 to 40 seconds. So we want to stay in that same, we want to look at B. So we, instead of A, we're going to look at B. So it would be the 0.7 moles of B minus the 0.46 moles of B divided by 40 minus 20, final minus initial. And you would see you get the same time frame. So 70 minus 46, 0.46 is 0.24. I should have known that. So 0.24 moles of B divided by 20 seconds. So we're going to get a same rate of 0.012 moles per second. But this time it's positive, and the reason it's positive is because, again, A was turning into B. A was going away and B was making. And this was a 1-to-1 ratio. For every one of those disappear. So it makes sense that the rate should be the same. It was a 1-to-1 ratio, and so it should be going at the same speed as one another. All right, that's rate. Not hard. Okay, and so this is just saying what I just said. A is going into B, and so the rate of disappearance of A is equal to the magnitude. Magnitude just means number, but opposite the sign and the rate of the appearance of B. And so basically they're equal to one another, kind of like this. So the minus change in the amount of A divided by time equals the, so this is kind of neat. So they're setting equal to one another, and that is a true statement. Okay, that is a true statement. Again, negative because he's going away, positive because he's forming. All right, so let's try this one. So it says, calculate the number of moles of B at each time. So I'm going to write moles of B down here. All right. So a 100 milliliter flask is charged with 0.1 moles of A. So we're starting out with 0.1 moles. And then that's all it said was there. So in the beginning, this was 0. Okay, they didn't say any B was there, and I've got A going into B there. So we've got seconds, and so now we've got 40 seconds has gone by. So how much? Well, if we started out with 0.1, we need to always keep 0.1 in there. So this would be 0.033, because that's going to equal 0.1. And then this would be and hopefully you're seeing that this would equal 0.1. because if whatever it's losing here it's always keeping that same amount in there. All right. Does that make sense? So that's my answer to that question. I just think it's easier to do it underneath there. Okay, now let's look at B. All right, so it says, calculate the rate of disappearance of A. Okay, let me get that where I can see it. I want to see that top part there. So I'm doing this problem. I'm going to work it up there so we can still see the top part here. So between 40 and 80 seconds. So here and letter A. So I'm wanting here. And some of you are already starting to work this, and hoping you are, but actually I'm hoping you're not. But it wants it in big M per second. Big M is not moles. Big M is molarity. And for Chem 2, and I know for some of you it's been a while since you've had Chem 1, some of you just, last week, but some of you a while. One of the main things I need you to carry from Chem 1 to Chem 2 is the concept of molarity. Molarity is moles divided by liters. Very important concept. It is concentration. So this table is in moles. It is not in molarity. So I must convert these to molarity before I begin. Okay, and that's kind of important to convert them to molarity before you begin. So I know the moles. I'm going to go ahead and do this one first because I need to do the second one. 0.045 moles of A divided by liters. Well, it's a 100 milliliter flask, so that is a 0.1 liter. So if I divide that out, I'm going to find it kind of just moves that decimal over to 0.45. That's going to be, hopefully you can see it's going to do the same thing on that one, but I'll go ahead and do it here. Okay, so now that's moles of B, molarity of B. So now I've got the final, and the final was the 0.45 big M minus 0.67 big M divided by my change in time. And my time has to be in seconds. So on Chem 101, watch your units, because make sure that you know what units they're going to want, because units are really, really important. So it's 80 minus 80 seconds minus 40 seconds, which is going to give you 40 seconds. So you've got 0.45 minus 0.67 divided by 40. And I'm going to get a negative y, because A is going away, 0.0055 molarity per second. And that is our answer. Now we're going to shift gears just a little bit and talk about stoichiometric relationships. Stoichiometric, if you don't remember that from Chem 1, is just basically the coefficients acting as mole ratios, and really that's all that is. So I have a generic formula. This is from the book, and I will tell you just as a disclaimer, I don't really like this so much, but I am supposed to teach you. It's not hard, but I'm supposed to teach you it stoichiometrically, but I'm going to show you another way to do it as well. So they're just showing you this. The capital letters are supposed to be the reactants and the products. So A and B are your reactants, C and D, capital letters, are your products. And then the lowercase letters are supposed to be indicating the coefficient. Okay, so this is just a generic thing that the book has made up. And so to put some sort of relationship between these, we already said these guys are disappearing and these guys are forming. So we got negatives going on here and positive rates. We're talking rates here. And rate is the change in the amount divided by the change in time. So if I were to want to compare all these to one another and set them equal to one another, their values, you would do something like this. And so if you'll notice, the change in A divided by the change in time, The change in B divided by the change in time, change in C divided by, so hopefully you see that. And then this is negative because these are losing, and these guys are positive because these are gaining. And I've just set them equal to one another, and then I've done something unique to them. I've put 1 over the coefficient. So 1 over the coefficient of this equals 1 over the coefficient. It's a way to put these related to one another. So basically 1 over A equals 1 over B of this 1 over C. So this is one way to show a relationship stoichiometrically with a reaction. So now that's the generic, so keep that in mind. And now we're going to go to an actual equation. And so here's our equation. 4 of these are equaling 1 of those, equaling 6 of those. So if I wanted to express those reactions in terms of their change in concentration, and that is how we're going to do that, I would make this guy negative, those positive, and then I could set them equal to one another. That looks like this. 1 over 1/4 of this guy's change in amount divided by change in time equals, and you wouldn't have to put 1 over 1, but it is 1 over 1 here of this guy, positive because it's forming, equals 1/6 of this guy. So this, and we just set them all equal to one another. And so that's how we can express the rate of reaction in terms of concentration of these guys. So easy peasy. And so if you look at my old homework that I have up, you got some practice of that. So how would you apply this? Well, you would apply it by working a problem. So here's an example. I'm going to show you 2 ways. I'm going to show you using this method, and then I'm going to show you using just proportions, which is what I kind of like to do. So I'm going to do it both ways for you can see it. Okay. Here we go. So it wants us to compare pH 3, so it's going at this rate. It is disappearing, so that guy's disappearing. And we're looking for the appearance rate of this guy, so which is H2. So out of this equation, I'm not really wanting to look at P4. So what I would do I would take this guy and this guy. Don't need that guy because I'm not using him, so I only use the pieces that I want, and I would set it equal, so I have a negative 1/4 of this guy's rate, and that's just change in amount divided by change in time, would equal 1/6 positive of this guy's amount, or rate I should say. So I just chose the 2 pieces of the puzzle that I wanted. So now I'm going to take those numbers. Now the fact that this is disappearing, that is negative. I know there's a negative there, but to make this work, it has to be negative as well. So watch this. So negative 1/4. And now for this, I'm going to substitute this, and I'm going to put this number in here. So then you would get negative 0.150 moles per second equals 1/6, and this is guy I'm looking for, and so you would let it be X. Okay, so now you would start working. I took a picture of that, so that's just going to have to stay there, so sorry about that. And so if I go to work that, and you would get, I'm going to come down here below all that stuff going on there, 0.0375, and that when we'll lose unit, well, we'll go ahead and keep units, moles per second. That's just that negative making a positive, combining that, basically multiplying that, equals now 1/6 of X, and to get X by itself, I'd multiply both sides by 6, because it's 1/6, and you would find that X equals 0.225 moles per second. And so that's how you would use that crazy little formula thing going on there. All right, that's one way to do it, and I'm supposed to show you that. I have shown you that. So now I'm going to show you how I actually do it. I actually do it using just using proportions, because to me, my brain it makes more sense for proportions. So I'm going to go back and come up here. Actually, I'm going to take a picture of it again because that way maybe I can get some of it to not take pictures of. Okay, take another picture of it. All right, so here's my reaction that I'm dealing with. There's my reaction. If you do it this method, you don't really need to worry about the positive and negatives until the end. You just deal with numbers. I just think it's easier. Because I think most of you could figure out this guy's going to be negative and those two guys are going to be positive because you're losing reactants and gaining products. So I'm not going to get trapped in the negative positive world. Okay, I'm just going to do the ratio of the two guys that I'm wanting to deal with. And so I'm wanting to deal with this, which is pH3, and H2, which is the other one. So those are the two I'm going to do. So first thing I'm going to do is I'm going to put a proportion, and I'm going to do pH3 on top, and I'm going to do H2 on bottom. And it could be opposite, it doesn't really matter. And I'm going to use these coefficients, those stoichiometric coefficients, those mole-mole ratios. For every 4 of this guy, I've got 6 of those. So that's just the mole-mole ratio. And I'm just going to now set it equal. I've got to keep it where pH3 is on top and H2 is on bottom. And now I'm going to put their rates. We know the rate of the one on top, so we know this one. And we don't know this one. And then I can just cross multiply. And so you would get 4x equals 0.9 mole per second divided by 4. And you're still going to get 0.225 moles per second. Now let's decide if it's going to be positive or negative. We are looking for H2. H2 is forming, so the answer should be positive because it's not disappearing. That's using proportions, and I feel like that's easier than setting it up, but I am to teach you how to do this and be able to recognize how to do that. Okay, hopefully that made sense. We're going to do another one. All right, maybe. There we go. Let me scoot it up some. Whoops, it went too far. Wrong way. My thing is not wanting to move without clicking. Okay, well, hopefully you can see that it's not wanting to move up there. So hopefully you can see that we've got 2 O3s, which is ozone, making 3 O2s oxygen. So 2 ozones making 3 oxygens. And so it says, what is ozone speed if oxygen is appearing at a rate of 6.0 times 10 to the -5 meters per second? Or not meters per second. You may hear me say meters per second because I'm used to physics. So molarity per second. So I'm going to set this up like you would if we were comparing. So I would say a -1/2 change in O3 divided by change in time would equal a +1/3 change in oxygen divided by change in time. So that's writing up that relationship. I know oxygen speed, so I know O2. So I would say 1/3 of 6 times 10 to the -5 molarity per second is going to equal a -1/2 of x. And so I would just now do the math. If I do this, I'm going to get 2 times 10 to the -5 equals -1/2 x. And I would multiply both sides by -2. And I would get x to be a -4 times 10 to the -5. We won't worry about 0.0 if we want to do sig digs. Molarity per second. Okay. Why negative? Well, Ozone's disappearing, negative. Y positive, oxygen's forming. Okay, so that's using the equation. So now let's look at it using the proportions. And whichever you prefer, doesn't matter to me. All right, so for every 2 ozones, I'm going to write ozone, O3, because sometimes you get mixed up. There are 3 oxygens, 3 O2s, equals, okay, which one do I know? I know oxygen, so this one will go here. And I don't know this. So cross multiply, you get 12 times, that's not proper scientific, but we'll go with it. 3x divided by 3, x equals 4, y0, times 10 to the negative 5th molarity per second. Positive or negative? We're looking for ozone. Ozone is disappearing, so it's going to come out to be negative. Whichever you prefer. Okay, whichever you prefer. Doesn't matter to me. All right. That is Kinetics Part 1.